Welcome to this lecture 14 of the course on polymer chemistry, and in this 14th lecture I plan to continue the discussion we had on the thermodynamics of radical polymerization, which is valid for other chain growth polymerizations as well, and we talk about the molecular weight distribution, and we will talk about different processes, different polymerization processes for radical polymerization. Let us just recap couple of minutes on the topics we covered in last lecture. We talked about the dependence on temperature, dependence of rate of polymerization and molecular weight on the temperature for radical polymerization initiated by different mechanisms: thermal initiator, photochemical initiator and redox initiator. And we, in summary, we knew that the initiation process is most lower and had the highest activation energy for thermal process, and also ED for thermal was higher than ED for redox than ED for a photochemical process. Now, you also remember in RP term there was plus half ED term on the numerator, and in case of Xn there was minus half ED term in the activation energy. So, between these three processes, thermal process, redox process and photochemical processes, thermal process, because ED is highest, it was getting affected by the temperature rise. The increase in the rate of polymerization was much higher in case of polymerization initiated by a thermal initiator, then redox initiator and then photochemical initiator. In case of molecular weight, again similar order, the molecular was getting dropped or reduced with increasing temperature, mostly for thermal initiated reaction, then for redox reaction, and for photochemical reaction, because ED is actually 0, it was actually going up mildly. For in case of photochemical reaction, we actually get slight increase in molecular weight with increase in temperature. Okay. And we were talking about the Tc sealing temperature and the equilibrium concentration of free monomer, and we got these two expression, and we from this expression we know that every temperature, typically what you do in a lab, you actually start a reaction, say in a beaker or in a round bottom flask, and keep in a oil bath maintained or some other aqueous bath maintained in a constant temperature. Typically we do reaction, polymerization reaction as well in a isothermal condition. Now, each temperature you can consider, your reaction temperature you can consider as a sealing temperature, and the equilibrium value of the free monomer concentration at that temperature determined by this value del Hp and del Sp. So, that reaction at the temperature will continue till the free monomer concentration reach to the equilibrium value of the free monomer concentration related to that temperature. And typically for the monomers which we know undergo polymerization process, this equilibrium value of the free monomer concentration is very low. So, we assume that the polymerization is easy and polymerization the monomers undergo almost quantitative polymerization or convert almost nearly 100%. If we increase the temperature of your reaction, then what happen? Me goes up. So, if you do a higher the reaction at a higher temperature, then equilibrium concentration goes up. That means your polymerization reaction stop at a higher free monomer concentration. So, if you choose to do in a higher temperature, then you will always land up in a higher amount of unreacted monomer, even if your reaction is complete or reached equilibrium. And if you keep on increasing the temperature, one temperature will come where the equilibrium concentration is equals to the free monomer concentration, pure monomer concentration. That means you can never polymerize at that temperature or beyond that temperature, which is 61 degree for alpha methyl styrene we just talked about. So, 61 degree the free equilibrium concentration of the equilibrium concentration of the free monomer for alpha methyl styrene was equal to the pure monomer concentration. So, at 61 degree or beyond 61 degree you cannot at all polymerize alpha methyl styrene, and as we can see that the Tc value depends, or the relation between Tc and Me depends on the values of del H and del Sp. And as I discussed at the last part of my last lecture, that delta S between polymer and monomer is basically change in entropy due to translation motion, vibration or rotational entropies, and the rotational and vibrational entropies of the monomer lost due to polymerization is actually gained in polymer. So, they do not take part or contribute too much in the del S value of polymerization. Is basically the translational entropy drop for the monomers, and which practically does not depend on the monomer structure. So, you will see that del S value is more or less same for most of the monomers, but del H value will change as we were discussing in last lecture, and that will depend upon the amount of stabilization, which could be due to resonance or inductive effect or by hyperconjugation or by the inter monomer complexes. If more stabilization means lower value of del H, which means lower value of Tc, and the higher the strain, that means higher is the energy of the polymer, again the lower is the magnitude of the del H value. Now, let us consider or let us compare few monomers and their del S value. Now, del S and del G 0, now so let us compare between these two values. Now, del H in this case is for pure monomer. Pure monomer is getting converted to a pure polymer, which is completely amorphous or slightly crystalline, where in case of del S, a 1 molar solution, it could be either of these two. You have to fix pure monomer converted to pure polymer, which is either completely crystalline or slightly amorphous, and del S you can also consider from pure to pure or a 1 mole solution of the monomer to a 1 molar solution of the polymer repeat unit. Now, in this context you can appreciate that del H value does not depend on the concentration of the monomer, whereas del S value does depend. Del S value is dependent on the concentration of the monomer. Now, let us compare the values between few monomers and see whether how the monomer structure contribute to the values of. Now, the simplest monomer is ethylene, and in case of ethylene this is from a pure gas to a polymer, solid polymer. This is 93 kilojoule per mole and this is 155. Compare these with vinyl acetate. Now, this value is quite high, this will be higher from any other because we are talking about this is a gas phase reaction. The gaseous monomer is getting transferred to a polymer. So, obviously drop in entropy will be much higher. These are negative numbers, sorry. So, it will be much higher. When you talk about the solution phase, then these values will be similar. This is minus 88, minus 110, acrylonitrile minus 76, minus 109, methyl acrylate 8 MMA minus 56, propene minus 84, 1 butene minus 84, isobutylene minus 48, 2 more, styrene minus 73 and alpha methyl styrene minus 35. This is minus 100, minus 104, 121, now you can see that these del H values are more or less same. Now, as I said that it will be definitely higher because you are talking about a gas phase reaction where gaseous molecules is converted to a solid, whereas this case is all liquid monomer you are talking about. Now, let us compare between first styrene and alpha methyl styrene. Obviously, this alpha methyl styrene have a much lower del H value. Now, that is because this polymer made from this 1,1 substituted alkenes are going to generate, when this pi bond is sp2 is converted to sp3, they are going to give lot of strain. If this alpha methyl styrene is converted to a polymer, obviously because of this presence of these groups, the polymer will be much more strained compared to the monomer, which is a planar molecules. There is no strain of these groups. Okay. So, this happens for most of the 1,1 substituted alkenes. The resulting polymers is have much higher strain compared to if there was no such bulky groups. So, as a result, alpha methyl styrene has much lower del H value compared to the styrene. The monomer stability is more or same between styrene and alpha methyl styrene. Similar case for MMA. MMA also a 1,1 substituted, and same logic can apply here because these are resulting in a strained polymer. The del H actually, the magnitude of the del H comes down. You can compare between the values between MA and MMA. If you compare between MA and MMA, they are very close. They are close, but MMA is having much lower, because in case of 1 substituted the strain is much more compared to if you have a only one substituted monomer. So, a polymer resulting from MMA will be much more strained compared to a polymer from just methyl acrylate. Okay. If you compare between say propene and acrylonitrile, so if you have CH3 and CN, obviously the resulting polymers which have similar strain. So, it determine the del H value is determined by the stabilization of the this double bond, and in this case presence of electron ordering CN group, this will be more stabilized. So, that value of acrylonitrile polymerization will be lower. So, that 76 compared to 84. Okay, so, anything you do to stabilize the double bond, it will lower the magnitude of the del Hp, and if you do anything which will increase the strain in the resulting polymer, that will also reduce the decrease in the value of del H, and as decrease in the value of del H, which means thermodynamic feasibility will also comes down. You can compare between say 1-butene and 1,3-butadiene. Obviously, 1,3-butadiene has much more stabilization, so it will have much lower del H value. If you compare between the acrylic acid and say acrylonitrile, now acrylic acid actually can form hydrogen bonding between the molecules, which actually stabilizes the molecules lower compared to when it get converted to polymer. If it compared polymers, these groups cannot line up to form hydrogen bonding. So, the hydrogen bonding in acrylic acid polymer is much lower compared to acrylic acid monomer, which means del H value will be lower for acrylic acid compared to say acrylonitrile. Okay, so, we talked about the stabilization of the monomer due to resonance, inductive effect, or by hydrogen bonding or dipolar interaction between the monomers, and increase in the strain behavior of the resulting polymer, which all these factors are against thermodynamic feasibility, because the del H value comes down. Now, the values for tetrafluoroethanol is very high, extremely high del H value, which is very difficult to, is actually 163. Trifluoroethylene is 163. Now, that is very high, it is very difficult to explain. It could be due to that resulting polymers have, because they have a strong association. So, this actually goes down, because fluorines are induce lot dipole moment. So, there could be an attractive interaction between the polymer molecule, and in this case that might go down, which could result in the increase in the magnitude of the del H. Okay, that is one way to explain the high value of del H, of high value of the magnitude of del H in case of trifluoroethylene to polytetrafluoroethylene, tetrafluoroethylene to polytetrafluoroethylene. Now, this value of del H is also important, because that dictate you the exothermity of the reactions, and if you have some knowledge about the exothermity, then you can actually control your, or you can take out the the heat generated, if the heat is, you cannot effectively remove the heat which is getting generated by this exothermic polymer reaction, then it will accumulate and it will increase the temperature, local temperature, it will increase the reaction rate and decrease the molecular weight in an uncontrolled way. So, having a knowledge of del H is very important for a chemical engineer, so that he can design a process whereby he can effectively remove the heat generated due to the polymer reaction, so that the reaction remain isothermal during the polymerization process. So, this alpha methyl styrene has the minimum of del H value, and of course, if you go back and see this one, if this is low for a given Me, this will be lower because this more or less same. So, if this goes down, Tc also goes down. If you consider this as a pure monomer, if you fix this consideration of pure monomer, then as this goes down, Tc goes down. Okay. So, which means that for a pure monomer, Tc is much lower for alpha methyl styrene compared to a styrene, which means that alpha methyl styrene cannot be polymerized, whereas a molecule like styrene can be easily polymerized to a very low equilibrium value of free monomer in the mixture. Now, we have talked about that 1,1 substituted disubstituted monomers also difficult to polymerize. We talked about in the initial lectures when we introduced the radical polymerization about 5-6 lectures back. For example, if you consider say malic anhydride, steel bean, or say 1,2 simply 1,2 dichloroethylene. Now, these monomers have quite significant value of del H. For say for malic anhydride, this is about minus 59 kilojoule per mole, which means it is not the fact that malic anhydride is very difficult to polymerize is not due to its magnitude, its value of del H polymerization. Now, what is the reason that these monomers are difficult to polymerize? That is because of if you have say polymer a monomer like this, where you have substituted 1,2 substituted and you have a radical approaching this double bond, which gets very restricted because of these substitutions. What is the radical it generates when it propagate? At the end, he is basically CH2Y, CH2, CHY, CHY and so on. This is the radical is get generated. Okay. This is the propagating radical. Now, when these has to further take part in polymerization, it has to approach this monomer. Now, that approach becomes very sterically hindered because of presence of all these substitution 1 substitution, and that is the reason this is very difficult, and that is why these reactions are very difficult to carry out. Now, so we talked about the Tc and the values of del H and del S. There is the Rp and Xn, the molecular weight can be also dependent on the pressure as well, okay, though it is not that significant as temperature. If the change in dRp says del V star by RT, you can write similarly activation energy in case of temperature, you can write activation volume in case of pressure. Depending upon the value of this activation volume is the change in volume from if the monomer goes from monomer state to transition state. If the volume is lower in transition state, then del V will be negative. If the volume of the transition state is higher than the monomer volume, then del V activation volume will be positive. Okay. If this is positive, then rate of polymerization will go up with temperature, and if it is negative, then it will go down. Okay. You can get it from this expression, and it is not very significant. The effect of pressure is not that significant for addition polymerization, and it is seldom practiced. The increase in rate of polymerization can be achieved much easily than by increasing the temperature than increasing the pressure. When you increased your temperature as much as possible, even if you do not get a appreciable polymerization rate, then people actually increase the polymerization, increase the pressure to get a higher polymerization rate. Now, let us talk about, we will not spend too much time on the effect of pressure on the rate of polymerization and molecular weight, because it is not that very significant. As I said, that effect of temperature is much more significant. So, you can, if you want to increase the polymerization rate, you can do it much easier way by increasing the temperature. If you run out of the option of increasing temperature, then people try to increase the pressure to increase the rate of polymerization. Now, let us talk about the molecular weight distribution in case of radical polymerization. Now, again, in case of radical polymerization, it is little complicated, because the molecular weight forms during different types of polymers are different. If you recollect the value for, say, your Xn, see, this is your average degrees of polymerization for a thermally initiated polymerization. Now, with time the value of m and I changes, okay, and changes mean decreased. As the more monomer is converted to polymers, the monomer concentration drops as well as the initiator concentration drop, but the drop in initiator concentration is much more compared to drop in monomer concentration. That means the molecular weight is more compared to the molecular weights which were getting generated before. So, if you consider this expression, with time goes molecular weight concentration of monomer drops, so as the concentration of the initiator. Now, the drop in I is much sharper compared to drop in M, concentration of M, which means that Xn, the average degrees of polymerization or the molecular weight, increases with time. Okay. So, which means that the molecular weight distribution, if you consider the entire reaction, is very complicated, because at any instantaneous time the molecular weight is different. If you talk about the molecular weight at the beginning of the reaction, that is quite different than the molecular weight of the polymers which are at the end of the reaction. One more fundamental difference in case of radical polymerization with the step growth polymerization, I spent some time in lecture probably couple of lectures back, that in case of step growth polymerization, the polymer is considered the entire mass. You start with the monomer, you complete the polymerization reaction, and you consider the entire reaction mixture is the polymer, which includes monomers, dimer, oligomers and high polymers, okay, high molecular polymers. Okay. So, that entire mixture is your polymer sample. So, the PDI you got 1 plus P, which is for the entire polymer, which includes small molecules as well as the high molecules. So, how did we get that? Xn bar, remember Xn bar was the number of molecules at t is equal to 0 and number of by divided by molecules at end of the polymerization. Okay, so, we considered all the numbers, all the molecules present in at the end of the polymerization, which includes monomer, dimer, oligomer and everything. Okay. So, which are considering the small molecules also as a part of polymers, and we are getting the polydispersity of 1 plus P, and we discussed that during the polymers there could be cyclic reaction formation, other side reaction for which small molecules generate, which result in higher PDI value of higher than 2. But in case if you getting a PDI value is 1 point less than 2 for a polymers which you have taken out from the solution, which means that the low molecular samples which might have left in the solution. So, you are getting the polymer precipitate from your reaction mixture devoid of the small molecules. So, basically you are narrowing your distribution. Okay. So, you are getting a less than 2 value if you have if you have a less than 2 value. Now, in case of radical polymerization, how do we define radical polymerization? How do you define the Xn is the total number of monomers reacted. I hope it is all visible, this is not very sharp pen, by total number of polymer molecules. Now, these are high molecular weight polymers, these are high molecular weight polymers which you isolate from after the reactions. So, this does not contain the unreacted monomer. Okay. So, that is the fundamental difference between XN in case of radical polymerization and in XN in case of step growth polymerization. Now, in case of step growth polymers, XN is considered at the end of the reaction, where in case of radical polymerization XN varies each time the dead polymer chains are forming. So, XN will vary with the time. What is the value of XN for radical chain polymerization? We will not go into very details into derivation. Say at low conversion, that means at the beginning of the reaction, low conversion X in bar is given by 1 by 1 minus P X W n given by 1 plus P 1 minus P, and X W bar X in bar is P d I given by 1 plus P. Now, these are for case if one polymer is formed from one kinetic chain, which means termination by disproportionation or by transfer. Okay. This apply to this. Now, this case P is probability that the propagating radical will continue to propagate and build polymer. So, P is not the conversion, unlike step growth, P is not a conversion here, P is a probability that a propagating radical will continue to propagate, that means continue to react with monomer, which will be given by the ratio of rate of propagation with rate of propagation plus rate of termination plus rate of transfer. So, a radical, a kinetic chain or a propagating radical can undergo 3 reaction. It can again react with the monomer and propagate, it can terminate, it can transfer. What is the probability? Is the probability given by the rates, rate of propagation divided by total rates, which is summation of propagation plus termination plus transfer. Okay. Now, in case for high polymers, for high molecular polymers, again the probability is always, the probability of propagation is higher, because that is why it is propagating. P also tends to 1, because it is making high polymer, high molecular polymer, that means it is undergoing more times of propagating reaction than a terminating reaction or a transfer reaction, which means probability is close to 1. Now, if for a polymer getting for polymers getting terminated by combination, that means one polymer is getting formed from two kinetic chain, obviously the distribution will be narrower and the molecular weight will be higher. So, x n is 2 by, instead of 1 by 1 p, it is 2 by 1 p, and x w is 2 plus p 1 minus p. So, p d I is 2 plus p by 2. Okay, so, these are, remember this is at low conversion, we are talking about the reaction has just started, reaction has not progressed too much. So, the concentration of monomer and concentration of initiator has not changed much. So, ratio of monomer by I to the power half is, this ratio has not changed much. Okay. At low conversion it will not change much. So, the molecular weight, the average number of degrees of polymerization, the weight average degrees of polymerization and the PDI is given by this expression. I am not going into details in the derivation of this process, it is a complicated process, whereas P is given by the probability of the propagating radical will continue to propagate and build polymer, which is Rp divided by Rp plus Rt and R transfer, where if the polymer is terminated by combination reaction, then it is gives by this, and as I said, for high molecular polymer P is 1. So, the PDI value will be between, this is 1.5 to the case where we have termination by disproportionation or transfer, this 2. So, it is expected that at low conversion the polydispersity will be between 1.5 to 2. Now, if the reaction continues, this value changes and it actually is become higher, because the drop in, as I said, drop in initiator concentration is much faster compared to drop in monomer concentration. So, the chain length, the degrees of polymerization goes up. So, if you consider the total polymerization, so obviously the broadness will be much higher. The reaction, the polymers made at the beginning will be lower molecular weight, comparatively lower molecular weight, and if you increase the temperature, if you increase the time, the polymer molecular weights will be higher and higher. So, you have a much more broader polymer distribution. So, if you at the end of the polymerization, if you consider the MW by Mn value will be quite high and it is typically between 2 to 5. Okay. You understand that at low conversion it was between 1.5 to 2, but at the temperature at the time goes up, the polymer molecular weights increases. So, the distribution actually goes up, starting from low molecular weights at the beginning to the high molecular weights at the end, the distribution goes up. So, you typically the value of PDI comes around 2 to 5, and if there are gel effect like gel effect and all these things where molecular weight shoots up at the end, because of the reason we talked about in the last class, it could end up a PDI value of 5 to 10, and if there are gel effect, then what happened, you know that branching might happen, and if branching happened between or the which results from chain transfer to polymer, if intermolecular chain transfer happen, then the PDI goes up further. For intrapolymer chain transfer, there is no change in molecular weight or molecular weight distribution either. So, if there are branching happening because of intermolecular chain transfer, as gel effect, then PDI goes up and it could be as high as 20 to 50. Basically, these are not the polymers you want. You want polymers which are as narrower as possible. So, that is why you would like to avoid this gel effect and branching and so on, so that you can get narrower and narrower. This is the most typical values of PDI you get from a normal polymerization radical polymerization reaction. Now, what I will talk about, that we talked about the effect of temperature, thermodynamics of polymer, different molecular distribution. Now, talked about how the polymers are done. Now, we talked about all the theory and principles behind the molecular rates and all this. Now, the practical part, how the monomers are usually polymerized in an industry scenario or in the lab. There could be several processes. You can do polymerization only with a monomer, and we call it a bulk polymerization. You can dissolve the monomer in a solvent and do the polymerization, then it is named as solution polymerization. You can disperse the monomers in aqueous phase and do the polymerization. We call this suspension polymerization. You can do it in a dispersed polymer, the resulting polymer, the produced polymer could be dispersed in organic solvent, and you can continue the polymerization as the polymers remain in dispersed. We call that as a dispersion polymerization, and you can do the polymerization in emulsion as well. We talk about each of these in brief, and we will spend most time on emulsion polymerization. And so, let us start about the bulk polymerization. Is, as I said, is the most simple or simplest polymerization. You have to take the monomer and the initiator which is soluble in the monomer. So, you take the monomer, you dissolve the initiator and heat the monomer, okay, to start the to initiate the reaction. And obviously, what is the advantage here? Advantage is that we have seen that the reaction polymer reaction rate as well as the molecular weight goes up with increase in monomer concentration, okay, which is not true for increasing initiator concentration. For initiator concentration, if you increase initiator concentration, rate goes up, but the molecular weight comes down. Okay, you remember the discussion we had just a few minutes back. But monomer, actually, if you increase the monomer concentration, both the reaction rate and the molecular weight goes up, and this is the maximum concentration you can do. You can get the maximum concentration of monomer if you do in a pure state. So, monomer concentration is high, so rate of polymerization molecule is high, and because you are not using any other chemical solvents or other things, this gives you high purity polymers and gives you minimum contamination of the product, and that can be applied in optical applications like CD and other things where you require very clean polymers. Obviously, this has lot of disadvantages. For example, because your concentration is very high, even at low concentration, even at low conversion, the viscosity goes up, because the medium the polymer is viscosity goes up, and as the viscosity goes up, you cannot stir the reaction medium very effectively, and if you cannot stir, you cannot dissipate the heat generated due to exothermic polymerization, and as a result, what happens, there is a local heat generation which actually can degrade your polymers, which actually can degrade the polymer molecules and can generate coloration in your polymers. Okay. So, viscosity becomes high and starings become decovalent, and at the end of the polymerization also, if the viscosity of the resulting your final polymer is very high, then processing also becomes very difficult. As we know that high monomer concentration gives high reaction rate, so heat generation is high rate, and as a result local heat formation takes place, coloration and degradation takes place, and we have discussed if you cannot dissipate this generated heat, then you can actually get a gel effect because the diffusion comes down. These are the disadvantage you can get from bulk polymerization. So, what is done? It is still done, it is still utilized for say making styrene, polystyrene, polymethyl acrylate, polyvinyl chloride. Typically what is done, you start the reaction and keep it at low conversion, so that viscosity buildup is not too high, not unmanageable, and then stop the reaction, take out the polymer and restart the reaction again, so that you can get high molecular weight, high rate of polymerization without building very high viscosity. So, you have to do actually stop start type reaction, where you start the reaction, stop up at low conversion, and then you stop and take the polymer out. Another strategy is taken for making sheets and all these things, that you make a pre-polymer which is not very high molecular weight. You make a pre-polymer, so the viscosity is not high, and then that pre-polymer is poured into a mold, say in this case sheet, and then you want to get the polymer in a final form of a sheet. So, you pour that pre-polymer into the sheet and then without stirring you do the reaction. So, the reaction rate will be faster and high molecular weight produced, and it will, you do not need to process it will become like a sheet. Okay. So, you are not aiming for processing this thing, or you are not aiming for heat management, all these things, you are not targeting that. You are taking this pre-polymer, putting in a sheet type mold and then finishing the polymerization. You actually gel effect is a beneficial for these things, so that you can make a high molecular weight and reaction get faster, and you get the final form, final polymer in terms of a sheet. Okay. So, these are the things, these are strategies are applied for in industry for using bulk polymerization. We move to solution polymerization, where you have require monomer solvent and a solvent soluble initiator. In this case, you require initiator to be in the solvent, and free radical kinetics, normal free kinetics applied. It could be homogeneous if the polymer formed remained in the solution. It could be heterogeneous if the polymer is insoluble and precipitate out once it forms. Once it precipitates out, it can form powder or granule. So, sometimes this polymerization is called powder or granular polymerization. For example, acrylonitrile in bulk or acrylonitrile in water, in this case it should be water. So, if you start polymerization acrylonitrile in water, polyacrylonitrile is not soluble in water, so it is precipitated out. So, you get acrylonitrile powder or granule. Obviously, disadvantage you had for your bulk polymerization, in this case you do not have those problems, because you are doing in a solution, then heat transfer can take place efficiently, because in a solution viscosity does not build up. So, there is no question of local heat formation, local spot formation, hot spot formation, and degradation of molecules, and thermal control becomes easier. Now, what is disadvantage? Obviously, you are doing a solution, so monomer concentration goes down, which means rate of polymerization becomes slower and molecular weights becomes lower, and unless if you do not choose the solvent very carefully, the solvent can participate in chain transfer reaction, reduce your molecular weight further. So, you have to be very careful. Now, of course, sometimes it is very difficult to remove the solvent quantitatively from the polymer. No matter how much vacuum you applied, it is very difficult sometimes, because solvents stick to the polymer. So, it is sometimes very difficult to take out all the solvents from the polymer quantitatively, and that is very detrimental for the properties of the final polymers. You do not want solvent to be contaminating your polymers. Now, of course, you cannot throw out all the solvents, you need solvent recovery and recycling, which is a very hazardous process. You are talking about organic solvent, so it is not very environmental friendly and the scientist friendly either. You do not want somebody working in the lab with huge amount of organic solvent, that is health hazardous as well as the environmental hazardous. These are the disadvantage for a solution polymerization, but still used for making polyethylene polyacrylonitrile or polyvinyl acetate. There is a third type of polymerization we are talking about, where it is heterogeneous polymerization. It could be suspension or dispersion. In case of suspension, monomer and monomer soluble water. Suspension polymers are nothing but bulk polymerization done in small volumes. You make this small volumes of bulk polymers distributed in a or dispersed in a aqueous solution. So, all the disadvantage of the bulk polymers should not be present here, because you are doing in a small volumes and small droplets, and because it is present in a surrounded by aqueous medium. So, heat dissipation is easy, viscosity does not build up, is not a problem. So, what you do, you dissolve, take your monomer and dissolve the initiator in the monomer, and then on that you add your dispersing medium, which is already heated in the temperature you want to do your reaction. So, you take the monomer along with your initiator, you add the preheated dispersing medium and then vigorously stir. Once you stir, these monomers containing the initiator will form droplets, and it will remain dispersed, because you have added in the reaction medium some dispersants which are typically water soluble polymers like polyethylene glycol, or some inorganic particles which actually get absorbed on these particles and prevent them to coalesce, okay, so that they remain in the as a dispersion form, because you have these soluble water soluble polymers or the inorganic particles which actually act as a stabilizer for these droplets. So, what you do initially is dissolved in the monomer, and then preheated dispersing medium is added, and vigorous stirring converts the monomer containing initiator into small droplets of 100 to 500 microns, and because the dispersion presents, which are very small amount, 0.1 weight percent, and because you are continually stirring, these actually stabilize the suspension. So, now you have the monomer droplets along with the initiator molecules as a small droplets which are dispersed in the aqueous solution. Now, you are doing the bulk polymerization in the small droplets. So, all the advantages of the bulk polymerization is remain still intact: high polymerization rate, high molecular weight, very pure monomers, and once the polymerization is complete, you can just filter out and get the final polymers in a bead form. Okay. That is why sometimes it called as a bead or pearl polymerization. So, you can maintain all the advantages of the high polymers, bulk polymerization, and you can get the polymers by filtration as a beads. Now, these beads should not stick each other, it should be rigid. If you want to isolate these polymers as a bead, then it should be rigid and it should not stick to each other. Now, that happens if your polymer glass transition is way above your room temperature, the temperature you are taking out. If your glass transition temperature of your polymer is close to that room temperature or little higher, then the polymer will be soft, and if the polymers are soft, then they will stick to each other. So, these methods is typically applied for the polymers which have the high glass transition temperature like methyl methacrylate and all these things. So, we will start from this point and talk about the dispersion polymerization and emulsion polymerization in the next lecture. Okay.